So the common ion effect is going to govern pretty much everything we do for the next 2 or 3 days. So the common ion effect says, consider the following solution of acetic acid. So we put, well, first off, do we remember that this is a weak acid?
Yes, of course we do.
It's a weak acid because it's not a strong one.
Yes.
That's the best way to define it. When you put it into water, it will dissociate, not a lot, but it will at least a little bit break apart into some H plus and some acetate ion. Not a lot, but at least a little. Okay. If acetate ion, so we're not adding more acid or anything, we're just coming along and we're adding acetate ion. According to Le Chatelier's principle, the equilibrium will shift to the left. So what we have here is we have a beaker and we have added HC2H3O2 or acetic acid. Most of this will just stay together in HC2H3O2, and that is because it's a weak acid. But some of it will be H plus, and some of it will be C2H3O2 minus. All right. If I come along now and I add sodium acetate, this is extremely soluble because everything in family 1 always dissolves and anything acetate always dissolves. So this is like one of the most soluble things that there is. So when I put that into it, I am adding some Na plus. That looks like Nat, but whatever. Na plus, but I'm adding a ton of that, right? Anything I put in completely associates. So look, this skyrockets up. Are we okay with that? According to Le Chatelier's principle, if I add to one side, I start to flow the other direction. Now, look at the consequences to what I really care about when I do that. If I move away from the products, what's happening to the amount of H plus? It's going down. And why do I care about what happens to H plus? All right, because it's tied to pH. So it's a very strange thing that I can have an acid, but I can add a salt, which has a common ion, and that salt itself is not acidic or basic, but it can change the pH of the solution. What change have we made? Has it become more or less acidic? Less. So, by adding a common ion to a weak acid, we will make it a more basic solution. They have named our principal for next year in case anyone cares. I don't know her, so don't ask Jamie Kent. That's all I know. Like, I know she's a girl.
Well, yeah.
And that's it. Well, there's some Jamies that are males.
Well, yeah, I know, but you just refer to her a lot as a she.
Oh, okay. Okay. I think I've seen her. Like, I know I would. I don't know what he just said, but we'll edit that out of the video. I'm pretty sure I know her because I have some friends at Adelia. All right. Anyway, moving on. Okay, here we go. Yada yada. That's the common ion effect. Next up. So the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So that's the definition of the common ion effect. And we don't necessarily care about the extent of ionization of the weak electrolyte. We care about the change in H plus or OH minus. That's what we care about. Good enough? Is anyone? Okay, never mind. People are writing. So I'll unplug this because I'm an idiot. Okay, good. Still a lot of people writing. I'll just stand over here and look pretty.
You don't even have to like just stand there.
Bisky. I just look good all the time is what he's saying.
You can only record 25 minutes. We established
Welcome to the show, Shaw.
I've never known that.
It's never been a thing. There was a message that Hayden and I read, but I swear it said 55.
It said 55 yesterday, 25.
Oh, it did say 25 today? Oh boy, we're screwed. Why?
So that way you can save your time.
Okay, I could pause it. I know what I'm doing.
Or they can all experience what class is like.
Yeah.
Hey, listen to the
Here we go.
science.
Oh, oh
Cut
my.
out the last half.
Are we ready? Woo!
Oh gosh.
Calculate the fluoride ion concentration and pH of a solution that is 0.2 molar HF and 0.1 molar in HCl. Okay, this is not really anything different than we've ever done, except we already have some H+. So, here we go. We have our HF. Let me see how I have this set up. Because it's going to be, hold on, it's right there. Okay. Whoa, what just happened?
You went too far backwards.
I did. Okay, here we go. We have our HF concentration, our H plus concentration, and our F minus concentration. Those, it's just an ice table, which we sort of abandoned before and will sort of abandon again very quickly. All right, the difference here is instead of just having your weak acid and then your X squared, is we do have some stuff to start with. So if you look, our initial of HF is 0.2, and then H plus, HCl is a strong acid, so it's completely dissociated, which means I have 0.1. And then F, initially I have 0. So that's so far the only thing that's a little bit different, and it's really not that bad.
Wait, what do we get the one for H plus?
Right there. HCl completely dissociates into two parts, H plus and Cl, and both parts concentrations are equal to the initial concentration. All right, now our HF is going to go down X, our H is going to go up X, and our F is going to go up X. You okay with that? Okay, the next part, just watch me do, but don't write it down yet. So this would be 0.2 minus X. This would be 0.1 plus X. This would be X. All right? You can actually write that. That's fine. I'm sorry. Go ahead and write that. All right. And then, based on this, I know my Ka expression is equal now to, no, that's on the bottom.
Oh, that's right. Okay. 0.1 plus X plus X. Or no, times X. Right.
All that jazz, right? I'm already missing X squared initial. That was a lot easier. Okay, this is the part that I would just do, like I would just watch me do. Okay, that was pointless. Here we go. So really, Ka is going to equal 0.1x. You okay with that? I'm just distributing the x in. Plus what? X squared over 0.2 minus x. And then we would solve for x. How fun does that look? It's not fun. It requires the quadratic formula. No, my friends. We're not doing that. Ever. Ever. You know why? There's definitely an easier way. Look at this number. Is this a large value?
Yes. No, it's a very, very small one.
Thank you. It's 0.12368.
My bad.
This means, remember, Ka is the definition pretty much of how much of it dissociates. Does very much of it dissociate? No. So it is weak, which means that x is super small. Which means, look, can I just round that to like 0.0001? Is that okay? Yeah. And it's not, this is not 100% true what I'm saying, but it's true enough for what we're doing. If I take 0.2 and I subtract 0.0001, that is now 0.1999, is it not?
You're right, it is.
What's too many? Okay, sorry. Whatever. What's the difference between 0.2 and 0.199? Statistically nothing. Because look at our problem. We would only use 2 sig figs. What is this number in 2 sig figs? 0.20. They're the same number. So, you are welcome to use the quadratic formula to solve for x. But we, the rest of the world, are not going to do it. So please look after I grab this. Actually, hand it to her. She'll take care of it. All right. Now, hand that to that redheaded kid. It's for him. I can just feel it. You don't know? It's fine. He's right there. I had a 1 in 17 chance. All right, here we go. So please look, my friends. Are you looking at the screen?
Yes.
Subtracting a really small number is meaningless. So I'm going to get rid of that. And look, subtracting a small number, what did I just say?
Very not worth it.
Is meaningless. So now my Ka is much simpler. Ka is equal to 0.1x over 0.2. That seems a lot easier. And now look. Hold on. That button. I already know Ka. It's 6.8, right? Oh, give me a break. So 6.8 times 10 to the negative 4 is equal to 0.1x over 0.2. So I'll multiply both sides by 0.2. And those cancel out. And now I have 0.1x is equal to whatever that was. Did anyone do that? 1.3436. And then I just do what? My answer is 1.36 times 10 to the negative 3. If we did the quadratic formula, I would be willing to bet, and don't prove me wrong, but I would be willing to bet it's like 1.36. Was there a number right here in your calculator? Like there wasn't? Oh yeah, it wouldn't be. All right, anyway, if we used it, we'd probably get like 1.362 or something. Like the 10,000th place would change, but the math would stay the same. Okay, so now this isn't really the answer I'm going to be looking for. I'm going to want to know the pH. So I take the negative log of this. Yeah. Yeah, to find pH. Did I do something wrong?
I'm just thinking like, okay, so
I see what he missed.
Oh, you are right. I'm sorry. So this is wrong. This is all right. I'm sorry, but you are correct. That wasn't X. Thank you. We now take 0.1 and add that, right? And then you get that number, and then you negative log it, and you're pretty much going to end up with a pH equal to 1. So this is, you add this, you get 0.10136. You take the negative log of that, whatever, or the negative LG, and you get 1.0 something probably. Okay, 0.99 to 2 sig figs. That would, was there more than 0.99? Okay, 2 sig figs. We essentially are at 1. Okay. Now, my friends, we just spent roughly 9 to 10 minutes doing something pointless to prove a point. That's all right. I can make a second video after I delete other ones. Yes. Yes. So the reason this is pointless is look right here. In this original thing, this was a strong acid, right? With a concentration of 0.1, which means that this HCl, the pH is 1 based on that. Adding weak acid changed it by like 1/100th of a pH, right? Is that significantly important? No, it's not. Okay, so here we go. We did this to prove this point. If you have a weak acid and a strong acid combination, the pH is just determined by the initial concentration of the strong acid. All right? You'll have a problem like that in the homework and on the test, where you have the opportunity to do all of that math we just did, and you'll still get the right answer probably, as long as you did everything right. Or you just take the negative log of the concentration of the strong acid. Yeah. Thank you. We literally found that the difference was 0.00136, which in 2 sig figs, we would cut it off right there, essentially. Go ahead.
So on the AP test, we found the answer on this to be 0.99. So would that difference make a difference?
No, not at all. You would get it 100% right. Okay, who's with me so far? Okay, so we've talked about 2 things, and it's okay because you came in late. The common ion effect, but we can't apply that because what's different here? Was there a common ion here? This was a weak acid and a strong acid, right? The first slide was a weak acid and its conjugate base.